Hey everyone, and welcome to this explainer. Today we're going to unpack one of the absolute most fascinating survival mechanisms hidden deep inside human biology. We're completely moving past the usual diet buzzwords and fitness trends, and instead we're looking at a brilliant biochemical logistics problem. We are going to answer a really profound question. Why does the body actually make ketones? Because as you'll see in our source material today, it is not just some random byproduct of burning fat. It's actually a highly coordinated, elegant solution perfectly designed to keep your brain alive when the chips are down. So, to unravel this metabolic mystery, here is our roadmap. First, we'll look at normal body energy metabolism. Second, the fasting energy crisis. Third, the blood transport problem. Fourth, how ketones provide the elegant solution. And finally, we'll uncover the liver's great irony. All right, let's dive right into section 1, normal body energy metabolism, or how the factory usually runs. Think of your body's energy system kind of like a giant biochemical seesaw, governed by two main hormones. On one side, you've got insulin, which completely dominates our fed state. You know, when you eat, insulin spikes, telling your body to use that glucose, synthesize glycogen for short-term storage, and pack away fat. But on the exact opposite side, we have glucagon, the ruler of the fasted state. When you haven't eaten for a while, like say you skip breakfast or you're deep into a fast, glucagon takes over. It promotes the breakdown of stored glycogen, ramps up glucose production, and triggers fat breakdown. It's this perfectly balanced system of storing energy and then releasing it right when you need it. So what actually happens when glucagon tells the body to break down fat? Well, it's basically a step-by-step demolition process. First, fat is broken down into triglycerides, which are then dismantled into fatty acids. Then, through a process called beta oxidation, those fatty acids are ultimately converted into a tiny molecule called acetyl-CoA. And this is absolutely crucial because acetyl-CoA is essentially the universal fuel currency of your entire body. Whether you're burning carbs or fats, the end goal is always to produce acetyl-CoA to make cellular energy. But here's the catch. Simply having a bunch of acetyl-CoA is not enough. You could literally have all the acetyl-CoA in the world, but to actually make ATP, the real cellular energy your body runs on, it needs a spark. And that spark is oxalacetate, or OOA for short. When acetyl-CoA combines with OOA, it enters what's called the TCA cycle. Think of the TCA cycle like a massive internal turbine. The combination of these two molecules turns the turbine and boom, you get ATP energy. It's a beautiful, incredibly efficient process. But it completely relies on OOA being there. Which brings us right to section 2, the fasting energy crisis. What happens to this perfectly balanced cellular system when the factory breaks down? This is where the biological drama really starts. When you fast, your blood sugar inevitably drops, but your body, and specifically your brain, still heavily demands glucose to survive. So to meet this demand, the liver literally pulls OAA right out of the energy turbine and hijacks it for a process called gluconeogenesis, which is just a fancy word for the creation of new glucose. But remember our equation? Without OAA, that TCA cycle turbine is completely blocked. So all that fat you're breaking down into acetyl-CoA suddenly has nowhere to go. It just rapidly accumulates in the liver. You've got this massive stockpile of fuel, but the turbine is shut down. Your body is making a desperate, calculated choice here. Keeping your blood sugar stable is so absolutely critical to your survival that it will willingly shut down its own energy turbine to do it. And this leads us to a massive logistics nightmare, covered in section 3, the blood transport problem. It is quite literally a biological traffic jam. Now, you might be wondering, if the liver has all this trapped acetyl-CoA, why doesn't it just ship it directly through the blood to the starving brain? Well, it can't. Acetyl-CoA is permanently grounded. Physically, the molecule is just too large to travel easily. On top of that, it carries a really strong electric charge, making it super unstable for free transport in the bloodstream. And the biggest problem? The blood-brain barrier. It acts like an incredibly strict VIP club bouncer. Because of acetyl-CoA's large size and electric charge, that bouncer absolutely will not let it inside. It cannot reach the brain under any circumstances. But biology always has a backup plan, right? Let's look at section 4. Ketones, the elegant solution or biology's ultimate shipping hack. Faced with a starving brain and totally stranded fuel, the liver steps up as a master logistics center. It takes all that stranded, bulky acetyl-CoA and begins repackaging it through a process called ketogenesis. First, it converts the acetyl-CoA into acetoacetate. Then it refines it even further into smaller,
way more stable molecules called beta-hydroxybutyrate, or BHB, and acetone. These are what we call ketone bodies. The liver has essentially taken fuel that couldn't be shipped and transformed it into a completely sleek new format.
And honestly, this definition perfectly illustrates the core message of our explainer today. This is the big takeaway. Ketone bodies serve as a transportable form of acetyl-CoA. They aren't just some random waste product. They are literally biological shipping boxes. The liver strips away all the bulky, charged limitations of acetyl-CoA and packages its potential energy into a tiny, highly mobile ketone that can easily cruise right through the bloodstream. So once these little ketone shipping boxes hit the bloodstream, they freely glide right past the blood-brain barrier bouncer. And once they're safely inside the brain cells, a biological unboxing happens. The brain takes that BHB, converts it back to acetoacetate, and then unpacks it right back into acetyl-CoA. And because the brain still has its own internal OAA, it can just feed that acetyl-CoA directly into its own TCA cycle to produce ATP energy. The fuel has successfully bypassed all the blockades. To put this into perspective, this transport system is astoundingly effective. After just 3 to 5 days of fasting, these tiny shipping boxes step up to supply a massive 50 to 70% of your brain's energy demands. In really prolonged fasts, that ketone dependency can climb up to 60 or 70%, with glucose just covering the rest. It is a heavy-duty, highly reliable emergency generator for your most vital organ. Which brings us to an incredible physiological twist in Section 5, the liver's great irony, the selfless factory. Think about everything we've just talked about. The liver breaks down the fat. The liver manages the crazy traffic jam. The liver does literally all the heavy lifting of repackaging the acetyl-CoA into ketones. So here's a really fascinating question for you. Why can't the liver use its own ketones for energy? I mean, it is absolutely swimming in them. Well, the answer lies in a single missing key. The liver completely lacks an enzyme called SCOT. This is the exact specific enzyme required to unbox a ketone back into acetyl-CoA. Because the liver doesn't have it, it is strictly a manufacturer, never a consumer. It's essentially like a master chef who isn't allowed to taste their own food. It meticulously prepares and pushes all of those precious ketones out into the blood for the brain, the heart, and the muscles, but it is completely incapable of dipping into the supply itself. So, bringing it all together, here are the core takeaways from today's explainer. First, we really need to reframe how we view ketones. They aren't merely byproducts of burning fat, they're an essential, highly targeted transport system. Second, ketogenesis is basically just a way for the liver to turn trapped acetyl-CoA into a highly mobile fuel. And third, this entire elegant process completely relies on the liver acting selflessly, literally sacrificing its own local energy potential to guarantee the survival of the brain during periods of starvation. It is truly a marvel of evolutionary logistics, a completely seamless adaptation designed to keep you alive when resources just vanish. Which leaves us with this final thought to ponder. If your liver quietly orchestrates this massive, flawless biochemical shipping network purely to keep your brain alive during a fast, what other incredible hidden survival mechanisms is your biology quietly holding in reserve right now? Thank you so much for joining me for this explainer. I highly recommend digging deeper into this source material. The world of metabolic science is absolutely fascinating. Catch you next time.